Bismillahirrahmanirrahim. Let us go into a new chapter. Okay, it is the linear differential equations. So what are differential equations? So differential equations are actually equations that involve derivatives. Okay, it is very important in mathematics. There are various types of differential equations, but in this course we will only learn or touch on how to solve the first order differential equations. Okay, the examples of the differential equation as given in our book, and you can see the order, okay, the order here representing on the highest power of the derivative. Like here we call it order 1 because we only have dy dx. This second equation we call it order 2 because we have a second derivatives there. And over here we also can have dy over dx power 2 degree 2. Right. So in our syllabus we will only touch the first order differential equation. So the first order, sometimes we call it linear differential equations, are given in the form of dy dx plus p is a function of x multiplied by dy equivalent to q as a function of x. So in this course we will look into two methods to solve these linear differential equations, okay, which is called the separable method and integrating factor method. So how to solve the differential equation using this first method? Okay, so this is a simple note given in our workbook, okay, such that we have, there you can see there is a dy dx in this line equation. We can use this first method provided that we can separate the variable y and the variable x, okay, and after that we integrate both sides and hence get the function in terms of a y equivalent to the functions of the z. So again we're going to use this method provided that we can easily separate the variables. So let's look at examples. So given in our workbook page 279, example 1, solve differential equation y over x equivalent to dy dx. So this is called differential equation because of that dy dx. Okay, so let's solve it. Solve, here it means that we would like to get dy as a function of x. Alright, so let's see whether or not, I'm rewriting it back here, okay. So it was dy over x equivalent to dy over dx. Let's combine the y with the y, the x with the x. It's good that the y is on the numerator value. So hence as we rearranging it, so we get 1 over x dx equivalent to 1 on y dy. Or you can also write it as 1 on y dy equivalent to 1 on x dx. Okay, so this differential equation can be separate. Okay. So and after that, in order to get the y, we integrate. So to get the y, we integrate both sides. So hence, using the knowledge that we have had earlier on how to solve the integral, so we have ln y. Okay, the c concept I'm going to put on the other side. So here we have ln x plus c. Okay, so don't stop there. Make sure that you should solve the y. Okay, so here looking back into the law of log, e power ln y is y. We would like to get the y. So meaning let's change it into exponent. Okay, so ln y equivalent to e of ln x plus c. Right? So there, applying the law of the log, e power ln y is y. And over there on the So to simplify, we need to use this law of the exponent. Okay, so over here we have e power ln x multiply e power c. Right. So you do know that e power ln x is actually x, and e power c, this is a constant value. I'm gonna call it c. So hence y is cx. So that is our final answer, okay, on how we solve this differential equation. Okay, example 2 now. Solve the differential equation dy dx equivalent to 1 minus y, given that the y is less than 1 and that the y is 0 when x is 0. Okay, let's do it. So I'm rewriting back the question. So that is the differential equation. Let's solve dy by separating the variables. Okay, we can only use it provided that we can separate them. So here, let's take the whole lot of this 1 minus y. Okay, and we have dx. Make sure that the dx is on the numerator and dy is on the numerator, dx over there. So we can actually separate our variable. Okay, good. And then what? And then to get the y, we need to integrate both sides. So let's integrate both sides. And over here on how to solve this integral, last time on the techniques of integral, let's use a simple u substitution. Let u be 1 minus y. So we need to replace everything in terms of the u. Okay, du dy is negative 1. So meaning dy is negative du. So let's substitute that. So hence we got integral of 1 over u, negative, right? Negative du, and equivalent to the integral of dx. So let's solve this integral. Okay, as we solve, this is minus ln u, right? And I'm going to put the c, the constant of integral, on the other side. So integral of dx, 1 dx is x. Let's put the c on the other side, c. Let's replace it there. Negative ln u, u is 1 minus y. So there we have got dy. Okay, there is no differential format, okay, up to that level, but yet you have to simplify this. So let us read this as a positive. I continue over here. So I'm going to read it as a positive value. So hence we bring it to this side, negative x minus c. This is a constant. It does not matter plus or minus c actually. Okay. So and then what? And then to get to this value, we need to change it into exponent. Let's introduce e. Okay. So hence we have e power ln of 1 minus y, e power negative x minus c. Okay. And from the example 1, we have seen that a property of the log is that if we have e power ln x, it is x. Okay, the law of our log. So we can pull this thing down. So hence it becomes 1 minus y. Okay, absolute value. That's right. So and the right side there, we can say that it is e power negative x multiply e power negative c, which is a constant, okay, using the law of exponent, right? Okay, there. And hence this is positive. So what is y? Okay, so meaning this is like 1 minus y is e power negative x. I want to call this as a constant value e, c. Okay, so let's reduce it because it's a constant. you can call it as a big C. Multiply C. So rearrange this. So we get y equivalent to 1 minus C e power negative x. Okay, for our answer. Or y equivalent to 1 minus C e power negative x. Right. And after that, we are given a boundary such that when y is 0, x is 0, let's replace it. Okay, we replace. So y is 0. This is to solve for the C, I guess. 0, 1 minus C e power negative 0. Negative 0 is actually 1. Okay, anything power 0 is actually 1. This is 0, right? Okay, so this is 1 in value. So hence we solve our C. Okay, we can say that the C is 1 in value. Alright, so hence what is our y just now? So y is 1 minus C is 1, so we only left with e power negative x. Or we can write it as y equivalent to 1 minus 1 over e power x. So that is our final solution. Next, let's look at this example 3 given. Find the general solution for r d theta dr equivalent to cosine square theta. So basically we are to get the theta maybe. Okay, so the variables are r and theta. Right, let's try it. So let us start with separating the variables. This is the question that I rewrite. Okay, when you are to separate the variables, make sure that the dr, okay, the partial fraction too, is on the numerator value. Right, so help me. So let's gather the data on the left side. So we have 1 on cosine theta, and we get the dr. I want to make it on the numerator value, so this r is 1 on r. Okay, so 1 on cosine is actually secant. So we have 1 on r dr. Okay, so far so good. Okay, oops, actually looking back into the question gives us as cosine square. Right, so sorry, it's supposed to be cosine square, so it's supposed to be secant square. Right, so then we are to get the data, we need to integrate both sides. Okay, after you have separated them, integrate. Okay, so looking into your formula list, the integral of a secant square is easy. Okay, let's integrate all. So, because it's actually given to us in our formula list. It is actually tangent theta. Look into your formula list. And 1 on r, dr is ln r. Okay, r must be positive. And we put the c on the right side. Okay, then how to get to the theta? Okay, so let's change it as exponent, introduce e. So we have e power tangent theta, and here we have e power of ln r plus c. Okay, so basically, okay, so here we can use the exponent. Okay, so this is the exponent, the law of exponent I meant, and we call this as simple constant big C. Okay, e power ln r, last time again in our basic knowledge of the law of the log, if we have e power ln x, it is x. Okay, the law of the log. So over here, this is actually R and we have the C. Okay, this is actually given in our workbook, but you cannot leave your answer like this. You have to get to the theta. You have to solve the theta. So let's continue from that. Okay, so how to get to that tangent theta? So again, now we would like to change it as a log function. Let's introduce ln, okay, on both sides. So hence we say that this is ln of this thing equivalent to ln of this thing. Why so? Because again, when we solve this, ln e power tangent theta, okay, another property of the log, ln e power x is also x. Okay, law of the log. So ln e power x is x, ln e power tangent theta, yeah, right, e is tangent theta. Okay, so on the right side we have ln of c times r. Where is c? Okay, so using a property of the log, we can see that this is ln c, ln ab. Again, the law of our log. If we have ln ab, it is ln a plus ln b. If you want like to separate the constant, so that it becomes ln c plus ln r. And ln c is a value of constant. You need to verify later on. I call it maybe c0. Okay. So we have tangent theta being ln r plus c0. So hence, what is your theta? So there the theta is inverse tangent of ln r plus c0. You are able to get your c0 if you know the initial value problem. Okay, so what is theta in terms of the r? But as of now, you can just leave your answer like this, c0 or c, no problem. Alright, so there. Let us do more exercises, okay, from the workbook. Okay, thank you for now.